solve problem 5.2c as a home exercise. Let's move forward. Now let's discuss that how can you find out the resultant of a non-concurrent non-parallel force system. In order to find out the resultant of the non-concurrent non-parallel force system, resolve the forces into its components using a convenient reference frame, say XY Cartesian frame of reference, and then you can say that the x component of the resultant force is simply equals to the sum of all the x component of the component forces, and the y component of the resultant force is equals to the y component of all the forces. And then you can find out the magnitude of the resultant force using the law of polygon or using the Pythagoras theorem, and you can also find out the orientation of the line of action of the resultant force, which is equals to tangent inverse of Ry over Rx. In order to find out the location of the resultant force, you can again use Varignon's theorem, which states that the moment created by the resultant force about any point, say point O, is equals to the moment the sum of the moments of all the forces about the same point. So if you are able to find out the perpendicular distances of line of action of each of these forces, so for example, if you can find out the perpendicular distance of F1 from point O, so simply multiply F1 times D1 and then multiply plus F2 times D2 plus F3 times D3, and the sum of these moments will be equals to the moment created by the resultant force. And using this equation, you can find out the distance D at which the resultant force must act. In many cases, it is little cumbersome to find out these perpendicular distances to the line of action of these forces. So easiest way is to resolve these forces into its rectangular components oriented along x and y axis, and then you can find out the moments of these resultant or component forces about point O, and it must be equal to the moment created by the resultant force. In order to strengthen this concept, let's consider problem 5.4, which states that determine the resultant of the three forces: this force, the weight of the dam, and the weight of the water. These three forces acting on the dam, and locate its intersection with the base AB. So not only you have to find out the resultant of these forces, but you also have to find out at which point the line of action of the resultant force intersects the base AB. The third part is, for a good design, this intersection should occur within the middle third of the base. So then you have to, in the last part, you have to check whether the line of action does intersect the middle third of the base or not. In civil engineering, middle third rule states that no tension is developed in a wall or foundation if the resultant force lies within the middle third of the structure. For example, if the width of the wall is, let's say, T, so each 1/3 part is 1/3 of T, this is another 1/3 of T, this is another 1/3 of T, and if the line of action of the resultant force is passing through this middle 1/3 of T, so then you can say that there will be no tension in the wall. And for example, for masonry buildings or tall masonry buildings, the width of the masonry wall is calculated such that the resultant of all the forces pass through the middle third portion of the width of the wall. So we have to check this condition for our case in case of dam as well. So let's try to solve this problem. First of all, let's find out the resultant force. For simplicity, I am calculating it. I am resolving each force into its components. So the x component of the resultant force is equals to the sum of x component of all these forces. The forces towards the right are taken to be positive, whereas the forces towards the left are considered to be negative. So Rx is equals to plus 10,000 and minus 6,000 cos 30. This is the x component of this force, and this is the y component of this force. So Rx comes out to be 4,803 0.8 pounds. The positive sign indicates that this force is acting towards the right. The y component of the resultant force is equals to the sum of all the y component of these forces. So minus 24,000 because it is acting downwards according to my sign convention, and upward forces are taken to be positive. Minus 24,000 minus 6,000 sine 30, and the y component of the resultant force comes out to be minus 27,000 pound. The negative sign indicates that the resultant force is acting downwards. The magnitude of the resultant force using the Pythagoras theorem comes out to be around 27,000 pound, and the inclination of the line of action of the resultant force is 79.91 degrees. So this is the graphical representation of the resultant force. This is the x component and this is the y component, and this resultant force, the line of action of this resultant force is at 79.91 degrees. The second part of the question is to find out the location of the intersection of line of action of this force with this base. So at which point the line of action of this resultant force intersects the base AB. So simply move this resultant force along its line of action using the principle of transmissibility, and when let's say this is the point at which the line of action intersects the base AB, and this point lies at a distance of x naught from point A. Then I can easily find out x naught using the Varignon's theorem, which states that the moment created by these resultant forces about point A is equal to the moment created by all of these component of forces about point A. So moment created by the resultant force is Rx will not create any moment because the line of action of Rx is passing through point A, so its moment arm is 0. The moment created by Ry is, so Ry multiplied by x naught, since it is creating a clockwise moment about point A, so I will consider this moment to be positive and counterclockwise moment to be negative. So moment created by the resultant force is Ry times x naught. Moment created by the component forces, so 10,000 pound multiplied by this distance. This distance is given in the problem, which is 6 feet, and it is creating clockwise moment, so it must be taken as positive. This weight of the dam is also creating a clockwise moment, so 24,000 multiplied by 7, plus this force is also creating a clockwise moment, 6,000 pound times sine of 30 multiplied by this distance. This distance is unknown. Let's call the distance of this component force from point B to be x1. So this distance would be 18 minus x1. Then the moment created by this component force, and this is creating a counterclockwise moment, so minus 6,000 cos 30 multiplied by this perpendicular distance. Let's call this distance to be x2. So you get this equation from the Varignon's theorem by applying the Varignon's theorem. The only thing is to determine x1 and x2. So let's consider this triangle. Let's consider triangle BED, in which sine 60 is x2 divided by 4, or opposite side divided by the hypotenuse. So x2 comes out to be 3.46 feet, and apply using cos 60 which is equals to x1 divided by 4, so x1 comes out to be 2 feet. Incorporating the values of x1 and x2 in the equation number 1, I can easily find out x naught, which is the location of the resultant force, and so it tells me that the resultant force, the line of action of the resultant force intersects at a distance of 9.56 feet from point A. So this distance is 9.56 feet. Now the third part of the question was whether this line of action is passing through the middle third of the cross section or not. So the total width of the dam was 18 feet. So each 1/3 portion is 6 feet, and the middle portion is, so the structure will be safe when the line of action will be in this region. in this region such that x is larger than 6 and smaller than 12. So the coordinates of this region is can be written in mathematical form like this. So our x0 is 9.56 feet, which comes within this range. So it means that the line of action of the resultant force indeed passing through the middle third portion of the dam. So the dam is safe. Okay, now let's move forward. Let's move to let's try to solve problem 5.3c. Problem 5.3c states that determine the resultant R of the three forces acting on this simple truss. Specify the points on the x and y axis through which R must pass. So not only I have to find out the resultant magnitude of the resultant force, but I also have to find out the intersection of the line of action of the resultant force on the x-axis, and also the intersection of its line of action on the y-axis. The origin of the coordinate system is at point O, so this is the x-axis and this is y-axis. Let's try to solve this problem. First of all, find out the magnitude of the resultant force. So Rx will be equals to sum of all the x component forces. Right direction force positive, left direction force is negative, so minus 25 pounds, and the x component of this force plus 20 sine 30, and the Rx comes out to be minus 15 kilonewton. Negative sign indicates that the resultant force is acting towards the left. Ry will be equal to sum of all the y component of the forces. Upward direction forces are considered to be positive, so minus 30 and the minus 20 cos 30 degrees. So the y component of this force is acting downwards, which is 20 cos 30. So this is the equation, and the y component of the resultant force comes out to be minus 47.32 kilonewton. So this is the graphical representation of the resultant force. This is the Rx, this is Ry, this is the resultant force. And let's say the second part of the question was to find out the intersection of the line of action of the resultant force with the x-axis. So now let's move the line of resultant force along its line of action such that it intersects the x-axis. So now the distance of the resultant force is, let's say, x0 from the origin, and then apply the Varignon's theorem, which states that the moment created by these resultant forces about point O is equal to the sum of the moments created by these component forces about point O, to find out x0. So the moment created by Rx will be 0, moment created by Ry will be clockwise, so Ry times x0, and moment created by these component forces, so this is creating a counterclockwise moment, so minus 25 multiplied by 5. The moment created by 30 kilonewton force, so it is creating clockwise moment, 30 multiplied by 6 plus 3, 9. So the total distance, perpendicular distance, is 9 meters. So 30 multiplied by 9. Then there is a vertical component of this 20 kilonewton force, and it is also creating a clockwise moment. So 20 cos 30 degree multiplied by 9 meters. So this is the perpendicular distance. Then the x component of this force, which is 20 sine 30, and this is the perpendicular distance, which is 5 meters. So 20 sine 30 multiplied by 5, and it is also creating a clockwise moment, so plus, with the plus sign. So this is the equation which you will get it, the moment due to component forces. Solve this equation to find out x0, and x0 comes out to be 7.41 meters. The other part of the question was find out the intersection of the line of action of the resultant force with the y-axis. So this was the resultant force, and this is the origin O, this is the x-axis, this is the y-axis. Now move the resultant force along its line of action such that it intersects the y-axis. Let's say it intersected at a distance of y naught. Now again apply the Varignon's theorem. The sum of the moment created by the resultant force about point O is equals to the moment created by the component forces. So in this case Ry is passing through point O, so there will be no moment created by Ry, and there will be only moment due to Rx. So Rx multiplied by y naught, and it is creating a clockwise moment, so positive. So Rx multiplied by y naught. The moment created by the component forces, we have already calculated it in the first part here, so it's exactly the same. Now solve this equation for y naught. So y naught comes out to be minus 23.392. So you can write it down in a vector form, the line of action of the resultant force to be 7.41 I unit vector minus 23.392 j unit vector. I have applied a negative sign. Why? Because I can see from the figure that there is the intersection is on the negative y-axis. Okay? So this is the origin, and the positive y-axis is in the upward direction, and the intersection of the line of action of the resultant force is on the negative y-axis. So that's why I have put the negative sign over here. So this is how you can solve it. Let's look at another example. For example, let's solve problem 5.3d. Replace the force system acting on the frame by an equivalent resultant force and specify where the resultant's line of action intersects the member AB measured from point A. So first of all, find out the magnitude of the resultant force, and then find out the intersection of the line of action of the resultant force on the member AB. So these are the two things that we have to find it out. So magnitude of the resultant force, the Rx component will be equal to sum of all the x component of the component forces. So the x component of this 35 pound force, 35 sine 30 plus 25 pounds, it will give me the Rx component, comes out to be 42.5 pounds. Then calculate the y component, which is equals to the sum of all the y components of the forces. Upward direction force is positive, so this is minus 35 cos 30 and minus 20 pounds. So the y component comes out to be minus 50.31 pounds. So this is the graphical representation of the forces. Rx is positive, so it is towards the right. Ry is negative, so it is acting downwards. This is the resultant force, and it is acting at an inclination theta. I can easily find out theta. Theta is equals to tangent inverse of Ry divided by Rx, which comes out to be 49.81, and the magnitude of the resultant force from the Pythagoras theorem comes out to be 65.86 pound. Then find out the intersection of the line of action of the resultant force. So let's say this is the member AB and this is the resultant force. Move the resultant force along its line of action such that it intersects the member AB, and let's say it intersected at a distance x naught from point A. Then apply the Varignon's theorem that the moment due to the resultant forces is equals to the moment created by the component forces. So the moment created by the resultant force is Ry times x naught, and moment created by the component forces, so this component is exactly passing through point A, so it will not create any moment. The moment created by this force, 35 cos 30 multiplied by 2 feet, clockwise positive, so plus 20 times 6 feet, and this force is creating a counterclockwise moment about point A, so 25 minus 25 multiplied by 3 feet. Solve the equation and you will find out that x naught is 2.1 feet. So this is the graphical representation of the intersection of the line of action of the resultant force at the member AB, and this is acting at a distance of 2.1 feet, and the magnitude is 65.86 pound, and the inclination is 49.81 degrees. Let's look into another example. Try all other examples as a home exercise, because the more you will practice, the more you will learn. Let's look into problem 5.3H. This problem: the design specification for the attachment at A for this beam depends on the magnitude and location of the applied loads. Represent the resultant of the three forces and a couple by a single force R at A and a couple M. Specify the magnitude of R. So this is a member which is subjected to these two forces, and this one force acting over here, and a point moment of magnitude 8 kilonewton meter. First of all, find out the magnitude of the resultant force at point A. Then also find out the magnitude of the resultant moment at point A. So now I am enforcing that the resultant must act at point A, right? So in the earlier cases, we were only interested to find out the resultant force such that the resultant moment is 0. But now we are saying that the resultant must act at point A, and there is a possibility that the resultant moment may be or may not be 0 at this point. So we have to calculate it. So we have to calculate, or we have to calculate two things: resultant force and resultant moment at point A. Or in other words, I can say that I have to convert or I have to find out the resultant force couple system from this force system. Earlier what we were doing, we were finding out the resultant force only from the given force system. So let's try to solve this problem. Resultant force, the x component of the force is sum of all the horizontal components. So there is no horizontal component of this force, there is no horizontal component of this force. This force is making an angle of theta, so, and this force is parallel to this member, and the perpendicular to this member is making an angle of 20 degrees with the y-axis. So let's find out the inclination of this member with the horizontal. So using the alternate angles, I can easily find out that this member is making an angle of 20 degrees with the horizontal. So this force is also making an angle of 20 degrees with the horizontal. So sum of horizontal forces, so there will be horizontal component of this force, which is 2 cos 20 degrees. So Rx will be 1.879 kilonewton. Positive sign indicates that it is acting towards the right. Ry will be sum of all the vertical components, so plus 3, minus 4, and minus 2 sine 20 degrees, which comes out to be minus 1.684 kilonewton. In vector form, I can write it down: resultant force is 1.879 I unit vector minus 1.684 J unit vector, and the magnitude of R from the Pythagoras theorem comes out to be 2.523 kilonewton, and the inclination comes out to be 41.87 degrees. Then I have to find out the resultant moment at point A, which I can again find it out by saying that the resultant moment at point A is equal to sum of the moments of all the forces about point A. Okay? So it's not any generic point, it's simply the point at which I am intending to find out the resultant moment. So the resultant moment due to 4 kilonewton force is clockwise, so plus 4 times 1.8. This force is creating counterclockwise moment, so minus 3 times 0.8. The x component of this force is creating a counterclockwise moment, so minus 2 cos 20 multiplied by this distance. We have to find out this distance, and this force which is creating a clockwise moment 2 sine 20 degrees multiplied by this is the perpendicular distance. So 1.8 plus 1.2 plus this distance. These horizontal and vertical distances you can easily find it out. So let's say this is the member of length 1.5 meters and it makes an angle of 20 degrees. So this length will be 1.5 cos 20 and this length will be equal to 1.5 sine 20. So simply incorporate the moment arms and find out the resultant moment, and the resultant moment comes out to be 14.876 kilonewton meter. The value is positive, it means that the moment is clockwise, and let's represent them graphically. So R is 2.52 kilonewton and the inclination is 41.87 degrees, and the moment which is acting on this cross section is 14.87.